Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is interesting binary, easy version. In this question, we're given an array of length n, and initially each element of A is either 0 or 1. So A is a binary array given to us. And in one operation, we can increase any element A of I by 1, and we can perform this operation as many times as we want, including zero number of times. Now our goal is to make the array adjacent distinct. Now what is adjacent distinct? So for each I, A of I should not be equal to A of I plus 1. So if we have an array like 1, 0, 1, 0, 1, 1, 0, 1, this is not adjacent distinct because these two elements are adjacent and they are same. So one possible way of making this array adjacent distinct is increase this element by 1. Now this array, no two adjacent elements are same, hence this is an adjacent distinct array. Now we need to find the minimum number of operations to make the whole array adjacent distinct. Now in the constraints, you can see that the number of test cases will be in between 1 and 10 raised to the power 5, and the value of n would be in between 2 and 10 raised to the power 5. And the sum of n over all the test cases would not exceed 2 into 10 raised to the power 5. Now the prerequisite to solve this question is dynamic programming. And before moving to the solution, let us once discuss the sample inputs. In the first input, we have n equal to 2 and both the elements are 0. So we can make this array adjacent distinct by changing this element to 1. And we need one operation for this, hence the answer is 1. The second test case is already adjacent distinct, hence the answer is 0. In the third test case, we have value of n as 4 and the array is 0, 0, 1, 1. We can make this adjacent distinct by changing this element to 1 and changing this element to 2. So the array is 0, 1, 2, 1. And we required two operations to do this, hence the answer is 2. In the third input, we have 3, 0, 0, 1. We can make this adjacent distinct by making it 1, 0, 1 because now no two adjacent elements are same and hence the answer is 1. Now let us move to the solution. So let us say we have some array like this 1, 0, 1, 1, 0, 1, 0, 1, 1. And we want to find the minimum number of operations to make the element adjacent distinct, right? So now to make the array adjacent distinct, what all do we need? We just need to ensure that my current element must not be equal to my previous element, right? For all the indices. And there are just three possibilities for each index. So it can be easily proven that we can make the array adjacent distinct by making the elements either 0 or 1 or 2, right? Because if it is 1, 0, 1, we can just make it 2, and then 0, 1, 0, 1, and then we can just make it 2. So by just choosing elements up till max of 0, 1, and 2, we can just make the array adjacent distinct. For a formal proof of why we can always create an adjacent distinct array by at max using elements up till 2, we can just see the written editorial. But for now, let's just go with that assumption. So for each index, we have three options, either make it 0 or 1 or 2, right? So can we apply something like VP and what else info do we do? So if I want to decide what I want to place at this particular index, all I need is what was at my previous index, right? If I know what was at my previous index and I have three possibilities for my current index, I can just run the DP and just calculate the answer for my current state, right? So let's say we are at this index I and my previous element was 1, right? So we could have either a 1 or a 2. The state 0 is not possible because we can only increment the element. So 0 here is not possible. Hence, the DP of this particular I 0 would be storing infinity because that is not a valid state for this index, right? Now, up till here, for like the number of operations required such that this much subarray is adjacent distinct and this element is equivalent to 1 is 0, right? Because this much array is distinct or adjacent distinct and the number of operations required would be 0. If you want to make this element is 2, the number of operations would be 1, right? Now, what would be the number of operations till this index such that I make current equal to 0? or current equal to 1 or current equal to 2. For 0, it would be infinity, right? Because I cannot decrease this one down to 0. For this one, it would be the number of operations required up till here, which are either 0 or 2. Now, for 0, the number of operations are infinity. For making it 2, the number of operation is 1. So, 1 plus the number of operations required to make it 1, which is 0. That is 0. So, hence the answer up till this index, such that this much subarray is adjacent distinct and this element is equal to 1 is going to be equal to 1. Now, if I make this 2, so I can take either the minimum of this much subarray such that this element is either 1 or 0. Now, if this is 1, the number of operations is 0, right? This is for 1 and this is for 0. This is for 2, right? So 0 plus the number of operations required to make this 2, it would be 1. So the number of operations till this index required such that this element is equivalent to 2, given that this much subarray is my adjacent distinct would be equal to 1, right? Now to generalize this, what are we doing? We're on some particular index IDX, right? And we want this particular current value to store over here. Now I have three possibilities. I just ask my DP function or my recursive function to tell me what is the minimum number of operations till index I minus 1, such that that previous element is equivalent to 0 and my current must not be equal to 0, right? Because if my current is equal to 0, then my current would be equal to previous and that is an invalid case. Plus the cost of making my current equal to this particular value, right? Like the cost of making A of IDX equal to current. Now, or the other option that we have is like I'll ask my recursive function that okay, what is the minimum number of operations required till index IDX minus 1 such that my previous element is 1 plus the cost of making the current element as the particular element. And that I can only do if my current is not equal to 1, right? And if my current is not equal to 2, I'll just ask my recursive function that what is the minimum number of operations I need till index IDX minus 1 such that the previous element is 2 plus the cost of making the current element equal to 2. And these are the only three possible states. So we'll take the min across all of these cases, right? And that will be our current DP state, right? Now C is just nothing but the cost to change A of IDX to this current value. Here I've just again mentioned what exactly dB of IDX current is storing. It is storing the minimum operations till the IDX index such that A of IDX is equal to current. So we just change this A of IDX to current. Now what would be the base case? The base case would be if IDX is 0, then if the, yeah, for the base case we would get when the IDX is equal to 0, right? Because we will calculate for all the other IDX from these transitional steps. Now, if IDX is equal to 0, then we're going to replace all of them by zeros, by the way. So if dp of 0, 0 would be 0 if a of 0 is equal to 0, otherwise infinity, because we cannot increment, like we can only increment. So if our a of 0 is equal to 1, we cannot just change this to 0 in any possible way, right? So we'll just set this as infinity. Otherwise, if this is equal to 1 and a of 0 is 0, if a of 0 is equal to 1, then the number of operations would be 0. If a of 0 is equal to 0, then the required number of operations would be 1. Otherwise, if for dp of 0 2, if a of 0 is equal to 1, the required operation would be 1 to make 1 equal to 2. And if a of 0 is equal to 0, the required operation would be 2. That's pretty much the whole solution. We can just calculate the whole dp array this way. And our final answer would be min of dp of n minus 1 0, comma dp of n minus 1 1 and dp of n minus 1 2. Right? Because this stores the minimum number of operations required till index n minus 1 such that the last element is 0 or 1 or 2 and we'll just take the min across all of them and that would be our answer. So yeah, that's pretty much the whole solution. Now let's once see the implementation. So yeah, this is the implementation in Python. Let's first see the implementation in C++. So we'll begin by taking an input of n, then we'll just take in the input of the whole array. We'll define our DP array and we'll just initialize all of it with infinity. Then we'll initialize dp of 0. So we'll run a loop from a of 0 to less than 3. So what this will do is If a of 0 is 1, it will start from 1, and we'll just set it to be j minus a of 0. So if a of 0 was 1, and when j is 1, it will set 0. When j is 2, it will set 1 operation required. And that way we'll just have the base case set up for us. Then we'll run a loop from 1 to n. Now this x is our current state. So this x is nothing but this current that we discussed here. And this y is are these three possible values of the previous number. Now if x is not equal to y, that means the current is not equal to the previous element, then dp of ix, that is the current element, would be the min of dp of ix comma dp of I minus y, that what is the minimum number of operations required till index I minus 1, such that the last element is y, plus x minus a of I, which is the required number of operations to change from a of I to x, right? And in the end, we'll just simply print the min of dp of n minus 1 0, n minus 1 1, and n minus 1 2. Now, the time complexity of the whole solution is big O of n because we are just doing 9 times an operation and we can just exclude the 9 because it's a constant. So it's big O of n time complexity. Now, let's see the solution in Python. So we'll begin by running a loop for each test case, taking the input of n and the array. We'll define the TP array as n cross 3 with infinity, which is 10 to 10 raised to the power 18. Now we'll define the base case. So this is the base case. So we'll run a loop from a of 0, that is what is at the a of 0th element, till 3 minus 1, that is 2. So we'll run a loop from 0, a of 0 to 2, and we'll set dp of 0 x as x minus a of 0. So if let's say x is 1 and a of 0 is also 1, we'll set it 0 because we need 0 operations. If x is 2 and a of 0 is 1, we'll set it as 1 because we need 1 operation. And similarly, for all the other cases, we can just have this set up for us, with the base case set up for us. Now we'll run a loop from 1 to n. Now this x represents the current element, that is what are we storing at the current index. And this y stores what was at the previous index. Like, was the previous element 0, or was it 1, or was it 2? Now if my current is not equal to the previous, then we'll set the current as the min of the current, comma, dp of I minus 1 y, that is what are the minimum number of operations required till index I minus 1, given that the last element is equal to y, plus x minus a of I, that is the required number of operations to convert this a of I to x. So if this a of I was 0 and x is 2, we'll need 2 operations. So this will be nothing but 2 minus 0, which is 2. In the end, we'll just print min of dp of n minus 1, which is equivalent to min of dp of n minus 1 0, n minus 1 1, and n minus 1 2. And that's pretty much the whole solution. The time complexity is big O of n because over here in this loop, we're just doing 9 n operations, and because 9 is just a constant, we can remove it. So the overall time complexity will be big O of n, and that's pretty much the whole solution. I hope you like that. Thanks.